Okay, so good evening, everyone, and welcome to today's live session. We are into the week 9 live session for the course Nonlinear Vibration, NOC25 me57. And this course is being taught by Professor S.K. Dwivedi, IIT Guwahati, and I'm Rashya Aditi Ranjan, NPTEL PMRFTA in the Department of Mechanical Engineering, IIT Patna. And we have already completed 8 weeks live session for this course where we have discussed various questions, concepts, and some problems related to the nonlinear vibrations, which has helped us in understanding the concept of nonlinear vibration, why it is important, how we can actually tackle a system with the nonlinearities present in it, etc. Okay, so coming on to the overview of this week. So, this week was not much concerned about okay, anyways. So you see, this week was not much concerned about nonlinear system, but more about numerical techniques. But the question is, why were we discussing so much about numerical techniques? I mean, what was the reason? Because we are into a course of nonlinear vibration and giving a whole week into understanding, not actually the whole week, about 60 to 70% of the lectures were more concerned about numerical techniques. So, what is the reason behind it? So, you see, since we have already discussed about the solutions of nonlinear systems, we know that there are two ways of finding the solution of a system. One was the numerical technique, and the other was the approximate analytical technique. Because when we talk about a highly nonlinear and a very difficult to solve system, getting a closed form solution is a very difficult and tedious task. And so what do? We either linearize the system or we do some perturbation up across the equilibrium point and then try to find out the approximate analytical solution. Or in order to get the exact solution, we try to use the numerical techniques in which we discretize our system and then we apply a numerical integration technique in order to get the exact solution of the system corresponding to different discretized values. However, why is it even important to discuss about the numerical techniques? I mean, we can just apply the numerical technique, right? Why is it even important? So, when we talk about numerical technique, we discretize our system, right? So, if I have a closed form solution, then if I want to know what is going to be the solution of my system from time 0 to time 10, I can easily find out the value. Whether my time is in integral value or it is in decimal. Like for example, if I want to find my solution response at 2.73678, right? I can find out. I'll just simply put that value wherever t is present and then I can get the solution. But when we are talking about numerical technique, we usually take our time domain, we discretize the time domain into n number of parts, where n depends upon how much accuracy we want, how much computational burden we can take up, and what are the specific values at which we should get the solution, right? Now, for example, if I take the h as 0.001, right, and my time varies from 0 to 10. Okay. So now, I can up to the third decimal, I can find out my solution, right? Because I'll get an array and then I can locate the point. But what if I want to calculate the value at t is equals to 1.768790? What about this now? See, this particular time does not exist in this exact value. It does not exist in my array, right? Because I have taken h up to third decimal place, right? So what will I do? I will have to round this off to three decimal places, right? And then what will I do? After rounding it off to 3 decimal places, I'll take whatever is going to be the value, then I can take out the response. Okay. So this is the problem that I have with the numerical technique, right? Other than that, there are several other problems as well, right? So which we will discuss as we proceed with the questions. But so if we talk about what was taught this week, so the discussion was about different numerical techniques for differentiation, integration, finding the root, and we're solving the differential equation. Okay, so for example, let us take an example of finding the root. Like, why do I even require a numerical technique, right? Now see, if I have a system dynamics given as, or maybe something like something like this. This is my equation of motion. So if I tell you that, okay, you tell me about the equilibrium points, okay, will you be able to find it? Definitely. What do you have to do? You have to make this zero, take this zero, and then you get a equation which is algebraic equation of the power 5. So you can simply evaluate the value, right? But now if I say that during the equilibrium, my equation is something of this type. If this is my equation, will you be able to find it, the roots? It is very difficult, right? I'm not saying it is impossible. It is very difficult to analytically find the roots of this equation because it has transcendental terms as well. It not only has algebraic but sine, tan hyperbolic e to the power x present. So finding out a root is difficult. So what would I do? I will take the help of a numerical technique to find out the roots of the equation. Okay. Now, in order to find out the roots, I will use some numerical technique. Okay, I'll about the convergence thing, I'll maybe talk about it when we'll solve the question because then it will be much relatable. Okay, so this is essentially the use. Similar is the concept for differentiation. If the equation is very difficult, it has many terms, and it is very, time consuming. So I'll take the help of numerical technique. Similar for the integration and for solving the differential equation, we already know the concept. Okay, now coming on to logistic maps. So, when we talk about the population growth, we try to find out a mathematical model by which we can tell that, okay, the population size actually grows following this numerical technique, following this mathematical model, wherein I can take the value of my initial population size and then I can predict about the my next population size. Okay, so the most famous um, equation is xn r into xn into 1 minus xn, where xn is what? Xn is my population size at the nth iteration, and xn plus 1 is the population size at xn, sorry, n plus 1th iteration, right? So if you can see that my xn plus 1 depends upon xn and r. So if I have the value of xn and r, I can keep predicting the mm, population size at n plus 1th iteration. Okay, so this was about logistic map, and then we use it to predict about my population size, how the population is growing. This is a very simple model. There has been modifications of this model, and so that to properly predict the population growth. But this one is a very simple model, and this very simple equation, discretized form of the population growth, it is going to show you everything. Okay, it is going to show you that how with the variation of the parameter r, your system can go from a steady state solution to chaos, that too following the period doubling route, and that we will see further also. So this is a very interesting map which we should learn, and from this we also learn to draw the cobweb diagram, which you can see in any of the nonlinear dynamics book. And third thing was about Poincare section and Lyapunov exponent, which we have discussed in the previous class only. So I will not be giving much time on it. Just to make you revise, Poincare section, what do? We decrease one dimension of our data. Okay, whatever the data we have, we decrease one dimension so as to know that for a 3D object or for a 3D variation of my system dynamics, how is the behavior going to be for a two-dimension slice of it, right? And when we talk about Lyapunov exponent, as I have discussed in the previous week's live session as well, that the Lyapunov exponent is nothing but a quantitative measure, right, which talks about the rate of convergence or divergence of my system from the original orbit if I give some perturbation, initial perturbation. And if my Lyapunov exponent is positive, we say that our system behavior is chaotic. If it is negative, we say that it is non-chaotic. Okay, so it is a quantitative measure, very important to basically quantitatively differentiate between chaos or chaotic motion and the non-chaotic motion. Okay, so coming on to question number 1. So the question number 1 says that the expression, this expression I'm talking about. We have an expression and we have to choose that this expression is used in numerical technique to evaluate what. For that, we'll first talk about very simple concept. Okay. So the concept says that, okay, let us say that my graph is something like this. And this is the plot of, okay. Now, since we are talking about numerical technique, the first thing that we will do is what? We will discretize my domain into n number of parts, right? Actually, yeah, okay. So we will actually like not n number of parts, n number of values. Like for example, if I divide my domain, this is my domain, and I divide it into 3 parts. So how many values do I have? 4 values. Likewise, if I divide my domain in n minus 1 parts, I'll have what? N values. Okay. So after discretizing my system, let us choose some arbitrary point, which is this xn. Okay. And the next point after this is going to be what? Xn plus 1, right? And the values, these are going to be my values, right? Now, if I say that, okay, I don't know what is the slope of my system, right? But I know the values xn from 0 to n, and I know the value of f from 0 to n. So how can I find out the slope, right? So when we talk about a right angle triangle, where we have a perpendicular, we have a base, and we have a hypotenuse, we say that this angle theta is equals to what? Perpendicular by base. Using the same concept, if I try to make a triangle over here, such that I'll just draw an exaggerated view, assuming that my xn plus 1 minus xn is very, very small than 1. Okay. Like this is the same concept, like if I take a circle and if I take a very small part of the circle, it is essentially a straight line. Okay, so same concept is used over here also, that if I have an arbitrary curve and if I take a very small part of that arbitrary curve, it is going to be a straight line, right? So with this straight line, if I try to find out the values, this is going to be xn plus 1 minus xn, and this is going to be f of xn plus 1 minus xn, right? And this is going to be nothing but the slope. This will be theta. So, slope is nothing but tan theta, right? So, if I want to find the slope at xn, f dash of xn, what will I do? I will just write, okay, this should be f like this. What will I write? I will write perpendicular, which is nothing but f of xn plus 1 minus f of xn divided by xn plus 1 minus xn. This is going to give me the slope at any xn. Okay, but the question is, why would I want this equation? Yeah, why cannot I maybe use the differentiation method, like the normal way that we differentiate equation in a continuous form? So again, the same thing. If my equation is something like this or even more complex than this, in that case, calculating the differentiation analytically is very difficult, right? It is very time consuming and it may also lead to error. Okay, so that time what do? We prefer the numerical differentiation, and from that we are able to compute the value of the differential. I hope this is clear. So this equation, if we talk about, it is used for nothing but to evaluate the differentiation. So for this, the expression this, it is the exactly same expression, is the numerical technique used to evaluate roots of a function f, differentiation of a function f at x k plus 1, no, differentiation of a function at f at x k. This is going to be your correct answer. Okay. Now the second question is, the differentiation of this at x is equals to 1 computed numerically is. So we have to compute the differentiation, that too numerically. Okay. Now here I will try to share the concept of convergence and accuracy. So our equation is 2.5 x square plus 1. Okay. We'll use a new slide. First thing, I have taken this simple equation because I just want to impart the knowledge. Okay, because if I'll take a very complex problem, it will be very difficult for me to make you understand, and for you also to perceive what I'm trying to make you understand. So we have to compute f dash of x at x is equals to 1. Okay, now first thing that I'm going to do is, since this is a very simple equation, so we will first try to find the differentiation in the continuous form that we do. So if I want to find f dash of x, which is nothing but d of f of x by dx, it is going to be nothing but 2.5 into 2x, which is 5x. So at x is equals to 1, this is the correct answer that I have. Okay. Now I will use the numerical technique. Okay. So for the numerical technique, what is the numerical technique? It says that okay, and xn plus 1 minus xn is going to be h. Let us assume. So this is the equation that we have. Okay, now we have to solve this equation. Firstly, it is very important to understand that choosing this h is the most important thing when we are doing any of the numerical technique. Not only for differentiation, any of the numerical technique. I'll write it also with red color. Choosing the step size h is a very important step for accuracy, convergence rate, and computational burden. Okay, so this is the thing. We have to choose h very wisely. As of now, we'll choose h as 1. Okay, and we'll see what effect is going to happen. So h is equals to 1, which means my xn is 1, xn plus 1 is 1 plus 1, 2. So my f dash of 1 is going to be f of 2 minus f of 1 divided by 2 minus 1. Now what is f of 2? It is going to be 2.5 into 2 to 4 plus 1 minus 2.5 plus 1 divided by 1. So if you see, we have 2.5 into 4, which is what? 10. Plus 1 minus 1 gone, minus 2.5 divided by 1. This is going to give me what? 7.5. Can you see? Can you compare this with this? And the actual value of the differentiation is what? 5. But the value that I'm getting by taking a step size of 1 is what? 7.5. If I talk about accuracy, the accuracy is very bad because it is giving me a value which is very much different from 5. If it would have been 5.5, I may have adjusted myself that okay, 5.5 is fine for me. But 7.5, if I talk about error, which is a significant value, right? So now then, let us try to decrease the value of h. Let us try to decrease the value of h, and we'll take h as 0.1. Okay. Now we'll take h as 0.1. In that case, my f dash at 1 is going to be what? Right? So in the denominator, I have 0.1, and in the numerator, I'm going to have 2.5 into 1.1 square plus 1 minus. So this is going to be, I have already done the computation, so I'll just write the value directly in order to save time. You can go and cross check it. Okay, so I'm going to get a value, yeah, 4.025 minus 3.5 divided by 0.1, 5.25. Okay. Now, if you remember, my exact solution was 5 and I'm getting the value as 5.25. In this case, my error, I still have a error of 0.25. I still have an error of 0.25. Okay, let us do one thing. For just trying, let us change h to 0.01. In that case, my f dash of 1 is going to be what? F of 1.01 minus f of 1. Okay, again, what we are going to get? We are going to get 3.55025 minus 3.5 divided by 0.01, which is something like 5.02, which I can nearly write as 5. Okay, now you can see that my answer is almost correct. Okay, but the question is that, okay, it's fine that by decreasing the h, my accuracy is increasing. That's a fine argument. Okay. In that case, what I can do is I can just keep decreasing the value of h, and I'll take the value of h like 10 to the power minus 6 or 10 to the power minus 12. But what is stopping me from doing this? The computational burden. You see, when I was doing this calculation, it was very easy for me. I could do it mathematically by my own. When I went to this calculation, I could do it by myself also, but I used the calculator. But when I talk about this, I absolutely require a calculator. That doesn't mean that I'm bad at mathematics. What that means is that giving so much time to calculating this thing is very difficult. And when we talk about, like, this was just one iteration, you see, just one iteration. It is taking this time. If we are talking about hundred, thousands, 2,000 lakhs of iterations, I cannot just sit and do that. If I'll keep doing that, then half of my PhD is gone in that only. So I use the like the softwares like Matlab. Now, if I'm using Matlab, if I give it such high accuracy task to do, either my Matlab is going to fail, it is going to show memory error, or it is going to take a huge lot of amount of time, right? And that time is what? It is costing me, correct? It is costing the energy, it is costing the time, it is costing everything. So when we decide the value of h, it is very important that we keep in mind that we choose h in such a way such that I get a good accuracy. Along with that, my computational burden is also not that much. Okay, my computational burden is also justified. I cannot let the computational burden to increase because it is going to what? It is going to take a lot of time, right? And it may happen that the software may get into a loop which it will never come out of. Yeah, then there is no other option to stop the code. So that is why it is very important that we choose H very wisely. As you can see, it directly impacts the accuracy, but it then also impacts the computational cost, and we have to optimize the value of H such that the computational cost is also reduced and our accuracy is increased. Okay. And then it depends upon the type of problem as well. If my problem is of high risk application, then I have to bear with the uh, computational cost because I'll have to give more uh, preference to the what accuracy. But if it is something which is of not that much catastrophic and it is something very simple for everyday use, then what we can do is we can decrease the computational burden, right? Like for example, if I take the example of a ceiling fan, like it is just giving me air, wind. It is uh, making a turbulence for keeping us cool. So you see, it is not something which needs a lot of accuracy. Okay, so what I can do is I can decrease the computational burden over there. But if I talk about an aeroplane, there the computational burden we have to bear because accuracy over there is very important. Even a small amount of change in the weather condition, right? It could adversely affect the aeroplane. And that is why we have to bear with the computational burden and we have to get as much accuracy as we can because it involves the human lives, and it is very important to safeguard that. Okay. So this is how we have to choose upon the application, upon what we need from the numerical method and everything, right? And this thing is applied on your numerical integration, it is applied on your finding the root, it is applied on your ODE, everything. Mind it, this argument is applied on every kind of a numerical technique. Your decreasing the value of step size is going to increase the accuracy but increase the computational burden as well. So we have to optimize both. Okay, I hope this is clear. We'll go to the second question now. So which of the following method may be used to obtain the integration of a function? Okay, so we'll do it very fast. Uh, if I talk about integration, what is integration? F of x dx integration from a to b. What do we do? We have a function. This is a, this is b, this is f of a, this is f of b. What do? We calculate the area under curve. Okay, clear. I hope this is clear. Now, this is easy for us if my f of x is simple. What if my f of x is again a very difficult equation, a nonlinear equation which has transcendental functions and everything in the denominator, in the numerator, everywhere? So what will I do? Then it becomes difficult to perform integration. So, and we have only a certain amount of rules and a certain amount of ways in which we can calculate the integration technique. Now, for that, we'll switch to what? The numerical technique. Again, in numerical technique, what do? We discretize our domain. We discretize we discretize the domain, calculate the integral at every point, and then what do? We just add it all and say that, yeah, this is the integration, right? Concept is very simple. If I take a very small part, this is nothing but a linear line. So if this is a linear line, then if you see this is a straight line, 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 I can simply apply simple formulas of triangle and rectangle area under the curve, and then I can similarly calculate for every kind of like for this, and I'm going to add it, right? Like this is one of my thing. This is the second one, third one. Likewise, every single uh, part that we are going to calculate the integration value and then we are going to add it, right? So we have discretized our domain. So the first kind of numerical integration technique that I would like to discuss is the Gauss quadrature method. You know what is a Gauss quadrature method? It is very simple. It is just the uh, discretized way of my integration technique. Like this is my integration. You know what is the discretized form of integration? Summation. Summation. n from, okay, no, we'll take I from 1 to n, and then I have wi f of xi, where xi is what? It is my node. Like this is my node, this is my node, this is this. These are my nodes. And what is wi? It is the weight function. Now I would say what is the point of weight function and everything. So we will discuss it further. Anyways, the weight function is such that, like for example, what I can do is I can discretize in n parts, equal parts, and then I can simply add it, giving one weightage to everyone. What I can also do is that I can discretize in such a way that I would like to give some more weightage to certain parts and less weightage to certain parts, right? For that, we can use the weight functions. Okay, so based on the Gauss quadrature, if I talk about the further three types of uh, numerical methods, you can see that this is the most generalized form for all the coming three type of integration technique. Second one is your trapezoidal rule. This is the most simple one. And trapezoidal rule, if you know about trapezoidal rule, this trapezoidal rule only clears the concept that why we are discretizing the domain and then we are adding it. Okay, so in the trapezoidal, yeah, so in trapezoidal rule, what do? We consider that my variation is linear. Okay, and the area that I have to calculate for my section, it is a type of a trapezoid. Okay, it is the type of a trapezoid. So if I try to plot it, this is A, this is B, this is f of A, this is f of B. Okay, now if I apply the trapezoidal rule, what does it say? Now you see my this trapezoid, what I can do is I can actually the if I talk about the area of a trapezoid, it is very simple formula, half into sum of parallel sides into distance between them. Okay, but we will try to do it in a generic way. We'll divide it into two parts. One is this part, another one is this part. Let us call it as 1, 2. So my whole integration int is going to be what? Area 1 plus area 2. Simple. Which is going to be what? Area 1 is going to be what? B minus A into f of A plus half into f of B minus f of A into what? B minus A. I hope this is clear. And if I take this 2 common and everything, it is going to be nothing but half f of A plus f of B into B minus A, which is nothing but the sum of parallel sides into distance between them. Right? So this is only my trapezoidal rule. It can be written in a generic form as h by 2 f naught plus f1. I discretize my system. I consider it as just a section with 2 points, f naught and f1. I evaluate the values at f naught and like the values f naught and f1, multiply it with what? H by 2, where h is my step size. This is my trapezoidal rule. If I apply the trapezoidal rule on one section and I do it for the other sections and just add it, it is going to give me what? The numerical integration. Now if I talk about, not this again, if we talk about accuracy, if I talk about accuracy, again, if we have taken only 2 points, accuracy will be less. So then comes the Simpson's one-third rule. Here we will do what? We will compute the value at 3 points instead of 2. Earlier in the trapezoidal rule, in one section, we were computing the value at what? Two ends. But now we will consider the third point as well, which is what? The mid of the two ends. Okay. So it is something like A, B, A plus B by 2. We'll compute the values F0, F1, F2. These are going to be the three values. What are we going to do? Nothing but for the integration, let us say I is equal to what? It is going to be H by 3. You know H? B minus A into F0 plus 4 F1 plus F2. Done. This is going to definitely increase my accuracy because instead of taking just 2 points, we are now taking 3 points in my discretized section. Okay. Then comes 4, which is the Simpson's 3/8 rule, which is going to give me much better accuracy. Here we take I as H by 8 into 3. Then we have f of A plus 3 times into f of A plus H plus 3 times into f of A plus 2H plus f of B. This is my Simpson's 3/8 rule. Okay, and here my H is what? B minus A by 3. B minus A by 3 because I have taken uh, 4 points. So 3 sections I have divided into. Okay, so if I talk about the answer of this question, all the 4 answers are correct. Okay, now we'll come to question number 3, which is the direct application of Simpson's 1/3 rule. Here we don't have the equation of f of x. We don't know what is x. We don't know what is f of x. However, again, this is a very simple equation and we can actually predict what is f of x. But for now, we'll consider we don't know f of x. Okay, so the question says that calculate the value of integration of a function from 0 to 2 using Simpson's 1/3 rule for the data values given below. Okay, Simpson's 1/3 rule, right? So for that, what I had to do, we had to divide. What? We had to divide our domain into 3 parts. If you remember, one was A, one was B, and the other one was A plus B by 2. Here already my system values that are given, it is given for 3 values, and my H is what over here? 1, right? My H is nothing but 1. Okay? No. Simpson's 1/3 rule says that I is equal to H by 3 F0 plus 4 F1 plus F of 2. My F0 is 0, F1 is 1, F2 is 8, and H we already know is 1. So my I is going to be 1 by 3, 0 plus 4 into 1 plus 8. 1 by 3, 4 plus 8, 12 by 3, 4. This is my answer. Now if I try to apply my analytical technique, if you see the values, you'll get to know that f of x is nothing but x cube. If I try to integrate x cube with respect to dx from 0 to 2, what do I get? X cube by 3 from 0 to 2. No, this is x cube. X to the power 4 by 4. Sorry. Yeah. So 4 to the power 4, for which we have 16 by 4, which is nothing but 4. This has actually helped me get the exact answer. However, it has given me an exact answer, that too for such high value of h, because this is a very simple equation, right? If I take a system which has much more nonlinearity present, the value of h should be taken in a very precise manner. Coming on to question number 4, the integration of the function this from 0 to 0.12 using the trapezoidal method is using the trapezoidal method. Okay, that is fine for us because we know the trapezoidal method. So our function f of x, what do we have to compute? We have to compute I, which is nothing but integration of okay. Let us try to first compute the analytical value. So we have this, which is dx. So we get integration of x twice of x to the power 4 by 4 minus x cubed by 3 plus 2x limits from 0 to 0.12. And 0 is going to be 0. Okay. So if I compute this, I've already computed, it is coming out to be 0.2395. You can recheck it if you want using the calculator. Now I would like to numerically compute. Okay. So for the trapezoidal rule, if I remember, I have to do nothing, but I have to just take the first value and the last value. So my f at 0 is going to be f at 0, 2, and f1 is going to be f at 0.12, which is going to be 2 into 0.12 cube minus 0.12 square plus 2, right? And h is going to be again 0.12. Okay, so if I put this, two minus 2 will be gone. So 0.06 into 3.9891 is going to be 0.2393. This is going to be my numerical answer. This is my analytical answer. So you can see that the error is not that much significant. The error is in the fourth decimal place, and that too just 2, right? So it is 2 into 10 to the power minus 4. It's a very small value, right? So the answer is going to be what? This. Never see here, it is already mentioned that you have to use the trapezoidal rule. Sometimes when they ask question, what do? They give the correct answer as well, so that you can choose the incorrect one. Always remember, if it is mentioned in the question that you have to use any numerical technique, whatever value that you are getting through numerical technique, you have to choose that, no matter if it's the correct answer or not. Okay, if it is mentioned that you have to use the numerical technique, use the numerical technique. Okay, don't get into going into the analytical method and finding the correct solution. Now the question is, find the root of equation this using the bisection method, for which first we have to talk about the numerical methods for finding the roots. I've already given an example earlier during the overview slide that why do we actually require finding out the numerical solution. Yeah, I've already told you that sometimes the equation is so difficult, it has the transcendental terms and everything, that getting the exact root directly using our mathematical skills, it becomes very difficult, and that is why we switch towards using the numerical methods, right? Okay, so as of now, I will discuss three methods, and I guess that is enough for you. After that, you can make your own ideologies also. Remember, you can also try to uh, use your own concepts to find out the roots. However, definitely the concepts that are given, they are the best that you are going to get. Okay, now I'll talk about the first one, which is nothing but the Newton Raphson method. Okay, so again, the Newton-Raphson method also uses the concept of, slope. So it says that if I have a system, I have this and this. I have the variation of f of x, something like this. Okay, let's just complete it. This is my xr, which is the actual root of the system. Now, you see here, if I choose a value, random value, because I don't know what is going to be the root. I'm considering that it's a very complex equation. I'm considering it's a very complex equation. So I'll choose a, oh, yeah, xn. F of xn is not equal to 0 is what I know. Okay. Now I will try to make a slope at this point. This. It is a slope at xn. Okay. And then I try to find out the equation of the slope, and then I try to find out this value x1. It is basically the point where my slope intersects the x-axis, and the value of y is 0. Okay. So if you remember, we had this equation f dash of xn was fxn plus 1 minus f of xn divided by xn plus 1 minus xn. Yeah. So this is the equation of the slope, correct? This is the equation of the slope. Now I put this 0. I put this 0, right? So then I'm going to get xn plus 1 minus xn is going to be minus of f of xn divided by f dash of xn. So I'll get xn plus 1 is equal to xn minus of f of xn divided by x dash of xn, right? I get that, okay, I have to use this equation. So if I put in the value of xn, I'm going to get xn plus 1. Again, I'll put in the value of xn and get n plus 1. I have to keep doing the iterations until xn plus 1 is nearly equal to xn. Until I see that, okay, now my xn and xn plus 1, every time I'm doing the iteration, it is not changing by a significant amount. So then I conclude that, okay, I have found out the value of my root. You understand the concept? Like I chose this, I made a line, and then I got this. Then in the second attempt, I'm going to make a slope like this. I'll get this value. Then I'll make a slope like this, and at the end, it is going to coincide with my xr. My iteration is going to coincide with xr. Okay, and I'm going to get the root. So this was my Newton-Raphson method. Now there is another method, which is the bisection method, which is by far my favorite method. But then if I talk about the numerical code for it, it is very difficult because every time it's a if-else loop that we have to give here. So if we assume that, okay, we'll consider two examples actually. One variation is something like this, other variation is something like this. B, A, A, B. What do we get to know? F of B is positive, F of A is negative. This is 0. Here f of A is positive, f of B is negative. So what we get to know is that between A and B, since one value is positive, other value is negative, there must be at least one root between A and B. There must be one root between A and B, and there could be many more. Okay, but one is going to be there, that we are sure. Okay, so if the root is there, but how will we find the root? The bisection method says that if I have 2 points A and B such that f of A into f of B is less than 0, then I get a new point C, which is A plus B by 2. Essentially, it's midpoint here. I get a new point A plus B by 2. What will I do? I will evaluate the value of the function at C. Okay. And once I evaluate FC, what will I do? I will do two things. F of A into F of C, or F of B into F of C. Either this is going to be true or the second one is going to be true. Okay. Only one is going to be true among the both. If this is true, I'm going to get another C1 as A plus B by 2. And if this is true, I'm going to get C1 as B plus C by 2. Okay, this is going to be the value of C1. I will keep doing this iteration until where? Until my Cn is nearly equal to Cn plus 1. I will keep doing this iteration till my this condition is satisfied. Once this condition is satisfied, I will say that, okay, I have reached the root of the system. Okay, so I'll compute this. Then if this is the case, we'll get a midpoint somewhere here, this one, then you see this and this, then we get a midpoint over here, then we get a midpoint over here. Like this, we'll converge to the XR, which is my root. Third method is the regular fallacy method. Regular fallacy method or the false position method. What do we do over here? Okay, so now again, I'll make a graph first. A, B. Okay, now again I have f of A, f of B. What will I do? I'll try to make a straight line joining f of A and f of B. I make a straight line joining f of A and f of B. Okay. Now, if I get this straight line and then I evaluate this point, the point at which this straight line, the value of y at this straight line goes to 0, I'm going to get a x1, right? For this x1, if I compute the actual value of f, it is going to be this. Likewise, I'll again make a straight line here, then again here, then this time again a straight line. Likewise, there will come a condition where my straight line, the value at which the value of y for the straight line will be 0 is going to be the same as XR, which is my root. So if I try to write it in the equation form, it is going to be y minus f of b is going to be what? Slope. F of b minus f of a divided by b minus a into what? X minus b. So what do I consider over here? I find the point where my y is 0. So I'll put it equal to 0. Okay, and then I try to find out the value of x. So I have x minus b is equals to minus of fb, b minus a divided by f of b minus f of a. So I have x equals to b minus f of b, b minus a, f of b minus f of a. Xn. Every time I'll keep doing this iteration till my again xn plus 1 is going to be equal to xn. This is clear. I hope this is clear. Now I'll come to the equation which is x square minus x minus 2. X square minus x minus 2, and I have to find out the roots. Okay. So we have to use the bisection method, which was the second method that we discussed, which said that first we had to find out 2 points A and B where my f of x is positive and at the other place it is negative. Okay. So first I'll try to compute it at 1. So f at 1 is 1 minus 1 minus 2, which is going to be minus 1. And if I compute f at 3, 9 minus 3 minus 2, 4. So my A and B are going to be 1 and 3. Now, okay, f of 1 into f of 3 is less than 0. Now, x naught is 1 plus 3 by 2, which is 2. F at 2, 2 square minus 2 minus 2, which is 0. The first root is x is equals to 2. This was easy. It converged very fastly. Okay, one thing also that I would like to mention over here, I'll again write it in red. The initial guess is a very important, as as the more the initial guess is near to the exact root, the less number of iterations will be required for convergence of the numerical technique. This you'll see now. In the last case, I chose 1 and 3, and in the first iteration only, my exact solution I was able to get. Right now, since you see this is a polynomial of second degree, we're going to have two roots. One root we have already found, another root we have to find. So now if I try to find out the value of f at minus 2, minus 2 whole square plus 2 minus 2, 4, which is positive. So what do I get? I get that f of minus 2 into f of 1 is less than 0, which means that there should be at least one root between -2 and 1. So I get x naught as -2 plus 1 by not 3, 2 minus 0.5. Okay, now I'll compute the value f at minus 0.5. It is going to be what? 0.25 plus 0.5, 0.75 minus 2 is going to be 0.75 minus 2, 1.25. 1.25, right? Now, 1.25 is what? Positive. Okay. At -2, my value was positive, but at 1, my value was negative, right? So it means that there is a root between what? No, it should be negative, no? Sorry, it should be negative, yeah. So at minus 0.5, it is negative, and at -2, it is what? Positive. So there should be a root between -2 and uh, minus 0.5. So again, I'll take x1 minus 2 minus 0.5 divided by 2. Minus 1.25. Again, f at minus 1.25 is going to be minus 1.25 whole square plus 1.25 minus 2. Yeah, it is going to be what? 0.8125. Now, this is positive at minus 1.25, and the value at minus 0.5 was negative. So, again, x2 is going to be minus 1.25 minus 0.5 divided by 2. This will keep on going. But you know what is interesting is that if I see the equation, what are its roots? -1 and 2, right? If you see for the first case, when we're finding out 2, like the value 2 of the root, it took only one iteration to find out. Why? Because we chose the value of my end points in such a way. Now, the way that I have chosen this point, I am already into the third iteration, and still we are not converged. Okay. So that is why I wrote the red line, that it also depends upon how we are taking the initial guess. The convergence is going to be faster if our initial guess is near to the roots, right? So, but then the question is that if we are dealing with a nonlinear system, we don't know what is going to be the root. So, it comes with maturity. When you will start doing this with the linear equation, then with the nonlinear equation, a bit of nonlinearity when you will add to the linear equation, then you try to do it. With time, you will develop that maturity to find out the initial guess. Okay. Now, question number 6. Okay. So we have to use the Newton-Raphson method to find out the root of this particular equation up to the third iteration. Okay. Reason that I have taken this question is that there are two informations that are already given in this question, which was not given in the previous question, right? First information, up to third iteration, which means that I have to only perform 3 iterations. I don't have to find the exact solution. Usually, when the iteration is not given, when do we stop the iteration? We stop the iteration when xn plus 1 is nearly equal to xn. In the subsequent iterations, this is always happening, so we stop the iteration. Okay. But if my equation is very complex, then it may happen that it will take a lot of time, right? So it is already given that we have to find out only up to third iteration. So now my computational time is decreased because I know that I have to do only 3 iterations. Second is the initial guess x naught is equals to 5 is given. The initial guess x naught is equals to 5 is already given in the question. So these both have made our life easier. Okay. Dealing with this question now becomes easier because if this was not given, it may happen that we would do some other number of iteration and if the initial guess is something far away from what we have to find, it becomes very difficult, right? So yeah, that is the thing. Now we will start doing it. Firstly, remembering what was the Newton-Raphson method. So if you remember the first method that we discussed for finding out the roots, that was the Newton-Raphson method, where we took out the slope, then we find out where my x n plus 1 was equal to 0, and then I was doing the iteration till x1 plus 1 was converging to xn. Okay, so Newton-Raphson method says that xn plus 1 is equals to xn. Let me see the equation minus. Okay, x naught is 5, right? And f dash of x, 2x minus 4. Okay, now we will compute the first iteration. X1 is going to be 5 minus f of xn, which is 5 square minus 4 into 5 minus 7 divided by 2 into 5 minus 4, which will come out as 5 plus 2 by 6, 5 point. This is my x1, the first iteration. Now we'll go into the second iteration. X2 minus. Okay, so I've already computed these to save the time. If you want, you people can recheck it. So we'll get 5.3333 minus. Okay, now coming on to the third and the last iteration, x3 minus. Okay, so you can also see that x3 is nearly equal to x2. So anyways, in the question it was given that we have to compute till the third iteration, but it is important to note that the third iteration also it also shows that my answer is also converged. The solution is converged. So my correct answer is going to be 5.31662. You see over here, the first option is correct, which is fine. But if you look at the second option, it is exactly equal to what my second iteration value. So if I don't do the iterations and the numerical calculations correctly, it may happen because if you see the variation is on the fifth decimal place. Okay, so if I don't do the numerical calculations in a very precise and accurate way, it may happen that I will mark the incorrect answer. Okay, so please take care of that while solving the questions. Okay, now we'll come out to question number 7. Okay, here I will briefly discuss about the how do we actually calculate the solution of a differential equation. Okay, since this is the very important thing specifically for us. So when we talk about differential equation, what is given to us? We have some f dash of x, right? It is given to us. We know this. Okay. Now this differentiation could be in terms of the coordinates or it could be in terms of the time, any of them. Okay. So if I have this and this equation is very tough, it is very highly nonlinear and it is not easy for me to solve it to get a closed form solution, I will switch to the numerical method. Okay. Now, which numerical method should I use? What should be the step size of the numerical method? How will I know whether my solution is correct or not? Okay. So firstly, we'll come into the concept. So the concept says that if this is f of x and this is x, and this is my plot. Okay. So if I want to calculate f dash of x at some point, this is my point xn. Okay. This I know. See, I don't know what this curve is. This red curve or blue. This I don't know what this behavior is. Okay. What I know is f dash of xn. I know that f dash of how f dash of xn is varying with xn. Okay. And from that I have to find out what f of x. Right. Now, if I know this value, if I know this value, then what I can do? I can again use the concept. Which concept? The concept of slope in a right angled triangle. So if I have a right angled triangle where this is xn, this is xn plus 1, so this is what? H, which is xn plus 1 minus xn. This is f of xn, xn plus 1, which is my unknown. And then I talk about the slope, which is tan theta, which is already known to me because I know f dash of xn. So what do I know? I know that tan theta is equals to perpendicular by base. So f dash of xn is nothing but f of xn plus 1 minus f of xn divided by xn plus 1 minus xn. Okay. So then what I can do is I can write f of xn plus 1 is equals to f of xn plus f dash of xn into xn plus 1 minus xn. Right? So from this, what do I get? I get that if I say that my f of xn plus 1 is yn plus 1, yn plus 1 is equals to yn plus 1 is equals to yn plus delta of xn into f dash of xn. Yeah, I hope this is clear. Okay, so this is what? This is my Euler method. This is my Euler method. Okay, it is the most simple kind of a method to find the solution of a differential equation in a numerical form. Okay, now again the problem is that how do we know that the solution is actually correct, it is converging, right? So there the h value that we take, it plays a very important role. Like for example, let us take an equation. I have y dash is equals to minus 10x. Y dash is equals to minus 10x. Okay. And I take h is equals to 1. I take h is equals to 1. And what I know is y at 0 is nothing but 1. Okay. Now I try to find out y at 1. What is it going to be? 1 plus minus 10 into 1, which is going to be what? Minus of 9. Okay. Y of 2 is going to be what? Minus 9 plus minus of 10 into 2, which is going to be minus 9 minus 20. Minus of 29. Right? Uh, Wait. Yeah, okay. F of x. Yeah, this is fine. Okay. Now if I compute y3, what is it going to be? It is minus of 29 plus, actually I'm doing it wrong, because when we are computing y1, it should be 0. Sorry. Wait, let me correct it. That is what I was thinking, that there is something which is I'm doing wrong. Okay, sorry for the mistake. Okay, so when we are computing y at 1, which is xn plus 1, we have to take the slope at xn. So the slope at 0 is what? 0. So we have 1. And if I compute y at 2, it is going to be what? 1 plus minus 10 into 1, which is going to be minus 9. Y at 3 is going to be what? Minus 9 plus minus 10 into 2. Right? It's going to be what? Minus 29. Right? Now if I try to see that how the variation is going, it is something like at 0 it was 1, at 1 it is again coming out to be 1, at 2 it is getting negative minus 9, at 3 it is getting minus 29. Is it correct? I'm applying a good numerical technique, right? Now if I try to find out the integration, Yeah, divided by dx minus of 10 of y. Shouldn't it be y? Wait. Actually, I don't exactly remember the example. Just thought maybe I just discussed. I think it should be just y. Because then only it is going to be y dy by y minus 10x ln of y minus 10x. So y is going to be to the power minus 10x. Yes. Okay. Should be y. Firstly, we'll compute and y definitely at 0 is going to be 1. Okay. Now, if I compute y at 1, what will I get? I will get 1 plus minus 10 into y at 0 is 1, which is going to be minus 9. Y at 2, which is going to be minus 9 plus minus 10 into y at 1, which was minus 9, is minus 9 plus 90, which is going to be 81. Y at 3, which is going to be 81 plus minus of 10 into 81. 81 minus 810. Anyways, it is going to be some negative value. So now if I try to plot it, how is the behavior of my y with x? So when my x was 0, my y was 1. When my x was 2, no, when my x was 1, y was negative, minus 9. Then it jumped to 81. Then it again came back to a very small value, right? What do I see? I see that my y has an oscillating nature and it has a characteristic of a diverging uh, behavior. Y diverging, oscillating between the positive and negative value. These are the two characteristics that I got to know. But is it correct? You see over here, y is equal to e to the power minus 10x. This is what? This is a negative exponential function. Firstly, it is never going to be negative. Secondly, it is a highly diverging function, converging function. If I see the plot of y with respect to x, it will be something like this. It is a converging function. It is never going to be negative. So I was using a numerical technique and it is giving me such blunderous answer. If I didn't knew that the integration of this is going to be this, I would have thought that whatever the numerical method is giving me, it is the correct option, right? Which is not true. So that is why it is important that we choose the value of h properly, right? That we choose the value of h properly. Now you'll see that if you reduce the value of h, if you reduce the value of h up till a certain amount, then you will get to know that it is going to give me the correct answers. It will start giving me the correct answer. So the problem that we were encountering is because of what? Because of the value of h, because we have taken a very high value of h, right? Very high value of h. Like if I take this only, 1, and if I take it's like minus 10h. For now, I don't know what is h. So y at 1, it should be negative now. Sorry, yeah, it should be greater than 0 now. That I know because of the physical character, like this exact analytical solution. I know that 1 minus 10h, which is the value of y at 1, it should be what? Greater than 0, which implies that 1, it should be less than 0.1, which should satisfy this. And hence, if I take h less than 0.1, it is going to give me better solutions. That is why it is important that we choose wisely the value of h, otherwise it is going to give us this kind of a solution, which is not true. Okay, so this was about Euler method. Then we have again uh, the RK4 method, which is what we have been doing using the OD45. It is based on the RK method. So what do we do in the RK method? So see, initially we were taking the value of slope at a point and we were just multiplying it with the h value and adding it to the yn value. But it was not giving us that good solution. So then this person came and he said that we should maybe take the value of slope at 4 values and then we should calculate the weighted average of those slope, and then we can get a better accuracy of the solution. Okay, and actually there is also one thing which is the degree of the convergence of slope, which I'll not get into because it is more mathematical. So it converges fastly to the accurate solution. So what do we do over here? So there we were calculating the slope at what? Xn and Yn. Here we will calculate slope at 4 points. What are those four points? First one is Xn, Yn. Second one is Xn plus h by 2, where h is what? A step size, comma, Yn plus k1 by 2. K1, what K1 is, I'll tell you. Xn plus h by 2, comma, Yn plus k2 by 2. And the fourth one, Xn plus h, comma, Yn plus k3. At these 4 points, I'll have to compute the value of slope. Okay. Now, K1 is what? H into f of Xn, comma, Yn. K2 is what? H into f of Xn plus h by 2, comma, Yn plus k1 by 2. K3 is what? H into f of Xn plus h by 2, Yn plus k2 by 2. And K4 is nothing but h into f of Xn plus h, comma, Yn plus k3. So we evaluate these four values, K1, K2, K3, K4. Then what do? We compute its weighted average. Delta Yn is going to be computed by the weighted average, which is going to be 1 by 6 of K1 plus 2K2 plus 2K3 plus K4. This is going to be my weighted average. And so my Yn plus 1 is going to be nothing but Yn plus h by, no, there will be no h because h is already multiplied, by 6 K1 plus 2K2 plus 2K3 plus K4. This is going to be the method. So this is nothing but by RK4 method, which is a very important method for us, especially because in the Matlab environment, we prefer using the RK method only. These OD45, these are all based on OD89, these are all based on the RK methods. There are various kind of RK methods. There's RK2 method also. Then the 8-9, it is based on the RK higher order methods. So this was the RK4 method. Likewise, if you are interested, you can take a good book of numerical techniques and then you can study about more about the RK methods. Okay, now coming on to question number 8. For the differential equation y dash is equals to x square plus 1 with the condition y at 1 is equals to 1 and the value of y at x is equals to 1.05 obtained by the fourth order Runge-Kutta method is. Okay. So we have the differential equation. Okay, I hope you people know that these differential equations, they are actually initial value problems. Why do we call it initial value problem? Because when we do the iteration, what do? We calculate xn plus 1 from what? Xn. If we if we want to start this iteration, we should at least know one value. Okay, one value which is at the starting of n. So that is why it is called as initial value problem, because for solving these kind of problems by numerical method, we should at least know one value of the initial value so that we could progress the iterations. Okay, so we have to compute at 1.05. So we'll assume that h is equals to 0.5, 0.05 only. Okay, because it is already a very small value. Okay, so we will start computing. First, we will compute k1, which is h into f of xn 1 yn 1, 0.05 into 1 square plus 1, 2 into 0.05, which is going to be 0.1. Okay, then we have k2, h into f of 1 plus 0.05 by 2, comma 1 plus 0.1 by 2. Okay, xn plus h by 2, yn plus k1 by 2. So this is going to be 0.05 into f of 1.025, comma 1.05, right? So 0.05 into 1.025 square plus 1, which is going to be 0.10253. I've already computed the values. If you want, you can recheck it. Sorry. K3, h into f of 1 plus 0.05 by 2, comma 1 plus 0.10253 by 2. But you know this yn term, yn plus k2 by 2, k3 by 2, this term is not of much use to us, because if you see y dash is essentially depending on only the value of x and not the value of y. So definitely our computation is reduced. If it would have been x square plus y square plus 1, then the computation would have been tough. Okay. So this is going to be 0.05, 0.10253 square. This will come out to be, yeah, it is going to be the same value as k2, because it just depends upon xn. So now we'll compute k4. This is going to be 0.05 into 1.05 square plus 1, which will come out as 0.105123. Okay, now I have the values of k1, k2, k3, k4. What do I have to do? I have to find out k, which is 1 by 6, k1 plus twice of k2 plus twice of k3 plus k4. it should be 0.10253. So this will come out as 0.615245 divided by 6. What is 0.10254? So y 1.05 will be 1 plus 0.10254 or 1.10254. Okay, I hope this is clear, and I hope now you understand also that how computationally difficult it becomes when we try to find out the values numerically by hand. So that is why we try to use the softwares for finding out the solution. Okay. Now I suppose the next question is, yeah. Now I'll connect with my laptop, since the other two questions are based on Matlab. I hope my screen is visible. Okay. So the question says that the value of x and y for the given system at t is equals to 100 is. Okay. So I have a system of equation given, and I have to find out that what is going to be the value at t is equals to 100. Okay. So which of the following options are correct? So as usual, I've already made the code, and here you can see this is the code. I've already put the equation, and now we will first see what were the initial conditions. So the first initial condition is 0.75 and 1.7. See here it should be y naught x naught and y naught y underscore naught y naught x naught y naught, which are the values of x and y at time 0, since these are all initial value problems. Okay, so the first initial condition is 0.75 and 1.7. Okay, so what we will do, we will, just a second. Okay, so we will do what? We will put these initial conditions 0.75 and 1.7. and we'll simulate the system. Let's see. Figure 2 shows the y versus x plot, and this shows the x and y versus the time plot. So you can see that over here, whatever we have given, these are the two values, okay? So how do we compute these two values? So the first way is that we take the cursor over here. See, it is showing me the value 5.90148, okay? Sometimes these are not correct, so what do? We write a command over here, this one, 1 and 2. It is going to give me the exact values at the end of the simulation, which is at t is equals to 100, which is what we have to find out. So the first one will reach the equilibrium 0.1863, and the second one is going to get stabilized at 5.9015. So let us see what are the options that are given. Yes, so this is the correct option for us. Okay, now coming on to the second one, where we have the initial condition 0.1 and 0.1. Now first let me close the figure. Sorry, first I'll have to run the code. Okay, so this is the phase y versus x, and this is my variation with respect to time. So you can see at t is equals to 100, the value of x is exactly the same as earlier, right? But if I talk about the value of y, it has now become negative. Earlier it was positive, now it has become negative. Okay, so I will now evaluate these values. See, 0.1863, exactly same as the previous case, but this has changed to minus 0.3817. Yes, so option B is also correct option. Now, if you look at option C, 0, 0 for initial condition 0, 0. We'll see that initial condition. Zero and zero initial conditions. See, now do you observe what is happening? The graph is almost same to that of what we obtained for the earlier case. Like not the transient one, but the equilibrium states are exactly the same. So for the initial condition 0, 0, the system does not remain at 0, 0. It again takes up the two equilibrium states. And again, if you want to check the values of those equilibrium state, what will you do? You will again call this command, press enter, and then you are going to get the values. Okay, so the third option is definitely incorrect. Okay, coming on to question number 10. Okay, now we have a logistic equation which has the third power of xn present in the equation, and we have to find out that what is the steady state behavior of the system for the corresponding values of r, which are the parameter values. Okay, so with this we will get to the concept of period doubling. So firstly, it is given already that we have to take the x naught as 0.1. Now you see this is not a ODE, this is not a differential equation, but rather it's a discretized equation wherein the xn plus 1 population size actually depends upon the parameter r and the population size at x nth iteration, okay, xn. It only depends on these two values, okay, and it is given that we have to consider x naught as 0.1. So this time we will not write a code for the differential equation, but rather we'll write a for loop like this. So for loop, the loop will work, the loop will keep computing the values till whatever value I have given. Like for example, here I have given for I is equal to 1 is to 10, 100, sorry. So it will compute for the 100 iterations. Likewise, I can make it 1000, 2000, any number that I want. Now you see, first option has the value of r as 1.3. Okay, let us run the code. See what is happening. So basically the x-axis is the number of iteration and the y-axis is the x value. So if you see that with the number of iteration, the x value actually stagnates to a particular value, right? So it has attained a equilibrium point. If I look at the option, system attains non-zero steady state for r is equal to 1.3. This is the correct option, and by mistake I forgot to remove this bracket. Anyways, this is the correct option. Now coming to B, system attain period 2 cycle for R 2.2. R is 2 point. Again, we'll run the code. Okay, so what is happening at every iteration, my value of population is either reaching an extreme value or it is either reaching a uh, minimum value. See, what you need to understand over here is that this is not a continuous graph. Like for example, let me do one thing. We'll plot it like this. This is not a continuous graph. It is just connecting. See, the actual variation is something like this. A positive maximum value, minimum value, maximum, minimum, maximum, minimum. For every iteration, it is either going to the maximum or minimum. So what is it? What is happening after every two iteration? It is repeating itself. At first iteration, it is here. Second iteration here. First like it is here, one iteration it is coming to the minimum, second iteration going there. So it takes every two iteration for the system to again reach the point where it was initially present, right? So in case of a discrete system, the period 2 cycle refers where the system takes two iterations to reach to the same point where it was earlier, okay, unlike what we talk about in the continuous system, the two period oscillation, okay. So here if it is taking two cycles, we call it as a two cycle periodic. So definitely it is a two cycle periodic, because if it is starting from here, it is taking two iterations to reach that point again. Okay, coming on to option 3, which says system attain period 4 cycle for R 2.25. 2.25. See, and this is the variation. So if you look over here, again we will do the same ideology, that how many iteration it is taking to again reach that point. So for example, it is at this point. Let us mark this point. Okay. After this, it is going here, one iteration. Second iteration, it is, yeah. First step, it is over here. Second step, it is over here. Third step, it is over here. And then fourth step, it is over here, which is the same place, same point where it was earlier, right? So you can see also 58 and 62. 62 minus 58 is what? 4. So it is taking 4 steps from 58 and is equals to 58. It is taking 4 steps to reach to the exact same point it was earlier at 58. Okay, so this is what? This is a 4-period oscillation. I hope this is clear. In the discrete system and in the continuous system, it is different. And do not get confused between the discretization of the system. Like when we have a equation, like we had the Duffing equation, there also we studied the period doubling bifurcation, and then you could give an argument that okay, I said that we are discretizing our domain and then we are applying the RK4 method. See, what we are doing is we are discretizing the domain, but we are keeping a continuous system as continuous only. Okay, we are integrating it with respect to time. Since we are not able to integrate it on our own, so we are doing the ODE45 we are using, which discretizes the system and then integrates it. That's a different thing. Here, our system is not continuous. It is a discretized system. You can see that we find the relation of xn plus 1 in terms of xn. Okay, so this is a discretized system only, and that is why the difference is there between the period 2 oscillation in case of a discretized system and in case of a continuous system. I hope this is clear. Okay, since we have already seen that from equilibrium state it goes to period 2, then it goes to period 4, so maybe we'll just change this and try to see if chaos is there or not. Okay, it is still period 4. Maybe we should change it to 2.3. Well, this is not chaos. If we see, it must be period 8. Uh, Let us just calculate 1, 2, 3, 4, 5, 6, 7, 8. Yes, it is taking 8 steps to see. You can see over here 62 and then 70. So it is taking around 8 steps to come back to that point. So what happens? Period 8 cycle. 0.5, and then we'll run the code. See. I feel that this is chaos. How will we check? Same thing which we used to do earlier. We change this to this, because for this initial value, chaos shows high dependence on the initial value. Okay, mistake. We'll apply a hold on first. See, do you see? Initially, the response is same, but after a certain time, the response, it shows divergence from each other. Let us do one thing. We'll take, okay, first we'll find this. Then we'll apply a hold on. And then we'll take, and then we'll run the code. See, this time we took 10 to the power 1, 2, 3, 4, 5. 10 to the power minus 5. Till here, the response is almost same, but after this, the response diverges, which shows that the response is what? Chaotic. So what do we see? We saw that for this kind of a logistic map that we have chosen, the system goes from equilibrium state to chaos through what? Period doubling bifurcation. Hope this is clear. over here. The first three options are correct. We'll mark it red. Sorry. Okay, so this was it for today. And I hope all the questions and whatever we have discussed, it is clear to you all. And if you don't have any doubt, we'll just end the live session. Okay, then we'll end the session and we'll meet next week again on the Tuesday. Okay. Okay, then thank you. Good night.